All right. That is the way I should be greeted every day, I think. Uh, that is our sound cue that this is sort of a huge big deal. You will see this little super strong man appear, letting you know this is really sort of one of those essential points. This is a huge big deal. This is a heavy lift, and this is something that will make us strong. We're going to be using this pretty much for the next 5, 6, 7 weeks. Um, so we'll talk about what the technique is. We'll talk about sort of why it works, and then we're actually just going to do it. That's how we're going to learn. So have plenty of paper and pencil around. Have your calculator ready. We are going to work on this problem solving technique, and it's really designed to change the units of something. So to change from talking about this material in one set of units into a different set of units. Eventually, we're going to use it to change from units referring to one material to units referring to another material, right? That's kind of the essence of chemistry. But we're going to do it by just simple multiplication, right? We're going to multiply whatever it is we start with by one or more conversion factors or relationships, right? How are these things related to each other to get to our desired quantity and unit, right? And eventually material when we get to that point of changing materials as well. So this really is kind of a huge big deal. It is probably the single most important concept or skill that you can walk away with because it's transportable. You're going to use it in pretty much any other quantitative sort of relationship. We'll use it in biology. We'll definitely use it in physics, engineering, nursing. All of your dosing calculations for nursing are really all dimensional analysis. They're all conversions from one kind of information into the desired information. So we'll be able to use this when we talk about a variety of different chemical concepts. All righty. So these conversion factors, these are the heart of what we're going to work with. They're relationships, proportions, connections. But here's what has to be. Here's what they have to be. They have to be true, right? So we can't have a conversion factor that isn't true, which means that there's going to be some conversion factors that we have to have memorized. There's going to be some that we look up. There's going to be some that we calculate from other information. Most of the ones we're going to work with right now are going to be ones that are memorized or ones that I have to provide for you. So they have to be true. So you have to have remembered them correctly, or you have to have written them down correctly if you look them up. And they are going to be used to change some number, some value, some measurement that's in one set of units to its equivalent version in another set of units. All right, so we've got two examples down at the bottom of our slide right now. So one is our horrible American system of units, 12 inches equals a foot, and the other one is our beautiful metric system. 1 centimeter equals 10 to the minus 2 meters. Both of those are true. Both of those are definitions, which means the numbers in both of them are exact numbers. Okay? What that means, right, if we remember back from last time, is that an exact number has no uncertainty, right? That means there is an unlimited number of significant figures, right? If we were to actually write these out the way they should be, we would have to write 12.00000 on into infinity, which we don't want to do. So we just have to understand and remember that 12 inches equals a foot is a definition of what a foot is. So the 12 and the 1, if we're going to use them in a calculation, 12 inches and 1 foot, those are exact numbers. Okay? Not every time we use the number 12 is it going to be exact, but in this case, it is an exact number. So let's just focus on the 12 inches equals a foot. Let's just look on that side for right now. So we'll put our eyes over on the left. And if we take that true sentence, that sort of math sentence, 12 inches equals 1 foot. And remember, with algebra, we can do anything we want to that 12 inches equals a foot as long as we do it to both sides. So if we divided both sides by 1 foot, not by 1, but by 1 foot, we would end up with the first part of that equality at the bottom. 12 inches divided by 1 foot is equal to 1 foot divided by 1 foot, which is 1, exactly, right? There's no unit there. The unit of a foot and a foot have canceled each other out, right? If we take that same math sentence, 12 inches equals 1 foot, and divide both sides by 12 inches, we're going to get 1 equals 1 foot divided by 12 inches. Okay? So 12 inches divided by 1 foot equals 1, and 1 foot over 12 inches equals 1, right? What's not true is 12 does not equal 1, or 12 over 1 does not equal 1 over 12. Right? That's not true. But when we put the units in there, it becomes true. All right. So here's the question. There's a question in the chat box. If the units cancel each other out, like they did when we did 1 foot over 1 foot, is it okay just to write the answer like just the number? And the answer is, of course. That is what it is. When the units cancel out, you're left with just a pure number. You're not left with a number that has a unit associated with it. Yep. But our units of foot and inches don't cancel each other out. They're not the same thing. So on either side, we've got 12 inches divided by 1 foot, right? And on the other side, we've got 1 foot divided by 12 inches. Both of those are equal to 1. What that means, right? If we remember what it means to have a 1, we can multiply by 1 all day long, and it's not going to change the size or the value or sort of the identity of the number that we start with. Right? So we can multiply by 12 inches divided by 1 foot, and that's not changing our object, right? It's just changing the units we're expressing it in. So we'll see that acted out. Right? And if we put our eyes now on the right side, we can take a look at that works the same way for 1 centimeter equals 10 to the minus 2 meters. We can divide both sides by 10 to the minus 2 meters. And we get sort of the first part of that equation at the bottom. 1 centimeter divided by 10 to the 2 meters equals 1, right? You'll note that the top, the numerator, and the denominator, the bottom, are the same thing. 1 centimeter that's on the top is exactly the same as 10 to the minus 2 meters. They're equal to each other. So as long as our numerator and our denominator are the same, whatever their units are, if those are equivalent in terms of those units, then we will get a value of 1. And if we divide both sides by 1 centimeter, then we'll get the other side, 10 to the minus 2 meters divided by 1 centimeter. Okay. Chemistry, I can tell you right now, the bulk of what we're going to be looking at, the bulk of our relationships, the bulk of our connections between things are going to look just like 12 inches equals 1 foot, or 1 centimeter equals 10 to the minus 2 meters. They're all there. We're going to have some definitions of things of how this amount of one thing is equal to this amount of the other thing. That's a relationship, right? If it's true, if we've understood the chemistry part of it, then that's a true proportion or conversion factor that we're going to be able to use numerically or quantitatively to do some calculations with. So that's where we're heading. Right now, our conversions, our relationships are going to be kind of dull, right? They're going to be things we remember, like 12 inches equals a foot, or some of our metric prefixes. We're going to work with those quite a bit today. So remember, there's 9 metric prefixes that you need to have memorized in your brain, so we don't have to keep looking them up. Again, we don't have them all done today. That's fine, right? Realize we're going to be working on that. And working towards that, not having to look that up. All right, how are we feeling about conversion factors and how we can make them equal to 1? Okay. All right, perfect. Okay. Let's hop to it then. Okay, so here is my little gecko. He is 24 inches long. Like, that's nice, but let's suppose I wanted to change his length into other units. So we're going to start at the top there. And can we agree that that first sentence is true? 24 inches times 1 equals 24 inches. Is everybody in agreement on that? Okay. I promise you, we're not going to do any weird math. Okay. All right. Now, some of you might be able, right? I can see in the chat box, some of you are already ahead of us, right? You can kind of see where we're going. You're like, well, I know what that is. I know exactly what that's going to be in units of feet or in units of something else. You're doing it in your head, right? You know that conversion. You've done it so many times. You know exactly how to get from one to the other mathematically. I want to show you the unit, why that works. Why does that math work? You've probably forgotten why it works. Okay. So again, if you're way ahead of us and you kind of already know where we're going, I'm going to challenge you to try and follow each step and see the logic in it. Right? What's important is the process, because when we get to conversion factors that we're less familiar with, that we don't see in our everyday lives, we want to have this process to fall back on. So when our conversion factors become things that are a little harder to wrap our heads around, or something that, like I said, we just don't do every day, I want you to have this process to see how it works, so you'll know that it will work no matter what our units are. That's the key there. This is super transportable. It doesn't matter what units we're talking about. This time we're going to talk about inches and feet at this point. All right. So 24 inches times 1 equals 24 inches. All right. I have not changed. You can see the size of my little gecko not changed at all. I multiplied by 1, nothing happened to it. All right. So instead of 1, let me put, can we agree that 42 divided by 42 is also 1? Is that, are we good with that too? Haven't done anything crazy, right? You'll note my gecko still the same size he was before. All right. And of course, 24 inches times 42 divided by 42 is still 24 inches, right? Again, my gecko, same size he was before. And we're like, okay, well, let's get a little bit crazy. How about instead of 42, we put 6 times 7? All right. I bet you didn't know you had to remember your times tables. All right. Can we agree that 6 times 7 is 42? All right. You know, we're still multiplying by 1. Can we see that? We're still multiplying by 1. It's 24 inches times 6 times 7 divided by 42, right? We still haven't done anything. The gecko still sitting over there at 24 inches tall, equals 24 inches. All right. And you're like, wow, these conversion factors are pretty boring. And you're like, yes, because all we're doing is multiplying by 1, right? We haven't done anything, right? Let's introduce our conversion factor that we had before. 12 inches equals 1 foot. Let's put it in there. Let's put that in there. Right? 1 foot is the same as 12 inches. So let me write it like this. I will write it with the 1 foot part on top and the 12 inches part on the bottom. All right. We are still multiplying by 1. You will note that my gecko has not changed size yet. Right? He's still the same size. We're just going to express that same size by multiplying by 1, and we're going to do a change of units. Right? 1 foot, that unit is the same as 12 inches. So in those parentheses, we're still multiplying by 1 because we have a true conversion factor. The numerator, 1 foot, and the denominator, 12 inches, are equal to each other. That's the same as multiplying by 1, right? Numerically, it doesn't look like 1, right? The 1 and the 12 definitely aren't the same. But remember, it's not 1 and 12, right? We're not multiplying by 1 over 12. We're multiplying by 1 foot over 12 inches. And that is equal to 1. Okay? So writing your units is what makes it true, right? If I wrote this as 12 inches times 1 over 12, that's not true, right? That's different, right? Then my gecko is going to shrink. And that's not what we want, right? We want them to be the same size. We just want it in different units. Okay. The work that you did on DP2 on the units was pretty good, being able to kind of follow those units algebraically. So if you look at the units in this expression, you can see that there's inches in the numerator, that 24 inches. That number we started with, we didn't kind of write it that way, but effectively it's in the numerator. So that 24, that unit of inches by the 24 is going to cancel with the unit of inches that's in the denominator of our parentheses. And we're going to be left with just the units of feet in the numerator. So when we do that math, right, 24 divided by 12, we don't have to put times 1 in our calculator. Our calculator gives us an answer of 2, but remember we should have 2 significant figures since I started with 24 inches, right? The 12 in 12 inches equals 1 foot. Those are exact numbers. Remember that's a definition of what an inch and a foot is. So we are limited by the measurement that we started with, in this case, 24 inches. So we have to add an extra significant 0, but we don't want to change the size of our value. So we have 2.0. So it's still the same size. You'll note my gecko is still the same size he was before. But we have an extra, not an extra one, the required second significant figure showing 2.0 feet. All right. What if we used our conversion factor, but let's use it the other way? It's still equal to 1 when we use it with 12 inches on the top and 1 foot on the bottom. Once again, my gecko has not changed size. I have multiplied by 1. 12 inches in the numerator is the same as 1 foot. That's in the bottom of that parentheses. I have multiplied by 1. Now, unfortunately, when I carry out all this math and look at my units aren't canceling like they did in the one above it, right? Can we see that those inches are both in the numerator, right? They're not going to cancel each other out. They're going to actually combine. We're going to get inches squared in the numerator, and we're still going to have that unit of feet in the bottom. And then we're going to have 24 times 12 as the number part of this problem. To 2 significant figures, we're going to get 290 inches squared divided by feet. And I have no idea what that unit looks like. I don't know what it means. It is correct. It is valid. We multiplied by 1. My gecko stayed the same size. He's sitting over there still the same size he was when we started this problem. But that answer isn't helpful, is it? Right? That's not a helpful conversion. We did convert the units from inches into inches squared per foot, but that's probably not what we were trying to do, right? So we were most likely trying to convert things into feet. So using our conversion factor, right? Choosing to use it in a way that makes some units cancel out and some units not cancel out, is what we're looking for. We're looking to do that, choosing that conversion factor, the correct one that relates the unit we start with the unit we're trying to get to. And we want to arrange it in our conversion, in our multiplying by 1, in such a way that some units are going to go away and some units are going to stick around. Both of the bottom 2 are valid. Both of the bottom 2, we have multiplied by 1 with a true statement, right? The top and the bottom, the numerator and denominator, are equal to each other. We did just multiply by 1. But one of them was helpful and one of them was not, right? So this bottom one, true, valid, but not helpful. So we want to, again, pay attention to our units when we're looking at our conversion factors. We want to use them in a way that makes sense. Again, you've probably done that conversion from feet to inches a bunch of times for whatever reason. And you already knew, well, don't I just divide by 12 or don't I just multiply by 12? Well, the answer is it depends on what direction you're going in. With this particular method, you don't have to remember, do I multiply or do I divide? The answer is, let me look at my units and they're going to help me decide how to arrange that conversion factor without having to think about any algebra, right? And it's much more efficient, right? It works with, again, any unit at all, any combination of unit, any series of conversions. So it's a very powerful tool. So if we can wrap our heads around how this works, we're going to be in great shape. All right. we have questions on my little gecko here? Did I do anything that upset you that we want to look at again? Let's look at this one more time. Just make sure we're going to look at it with our beautiful metric system. Oh, and a gorgeous cupcake. I should not have done this. I have not had lunch yet. All right. So let's suppose we have this beautiful, lovely cupcake with way too much frosting. And let's suppose it's 9.5 centimeters tall. Let's suppose we want to know how big that is in meters. All right. So we can do the same kind of thinking that we did before, right? So we can take our, right, 9.5 centimeters, multiply it by 1, and that's going to be equal to 9.5 centimeters. Yes? Yep. We're in agreement about that still? We can still multiply by 1 and not change anything. My cupcake has not gotten any bigger or any smaller. Yep. It's the same size it was before, right? So instead of 1, let's multiply by something that is equal to 1. Right? 75 over 75. All right. So the top again of my parentheses, the top and the bottom are equal to each other. 75 equals 75. Okay. So when I multiply 9.5 centimeters times 75 divided by 75, I'm going to get 9.5 centimeters right back. My unit hasn't changed because there's no units in the 75s. And my numerical value hasn't changed, right? Because I have effectively multiplied by 1. All right, let's do the same thing. Instead of 75, let's put in something that's equal to 75. 3 times 25, right? So again, as long as my numerator and my denominator are equal to each other, I am multiplying by 1. And I can do that all day long, and my cupcake is not changing size. I'm not misrepresenting what's going on there. I'm still talking about the same cupcake with the same height. All right. Let's use our conversion factor now, the one that has units in it. So let's see how that works differently. So again, remember, I have to multiply by 1. So my numerator has to equal whatever is in my denominator, right? Those two things have to be equal to each other. It has to be a true statement, or we're not multiplying by 1. We're multiplying then by something that's not quite 1. All right, so let's arrange it one way. Let's just put the meters on top. Okay, so 10 to the minus 2 meters is in fact equal to 1 centimeter. That's the meaning of the centi prefix. Centi means 10 to the minus 2. So 1 centimeter equals 1 10 to the minus 2 times a meter. Right? Basically just replacing that prefix with that power of 10 that we're remembering. Okay? So we are in fact then still multiplying by 1. Right? Again, we're not, if you look just at the number parts of it, you're like, well, we're not multiplying by 1. But we are multiplying by 1 because we're not just multiplying by 10 to the minus 2 and 1. We're multiplying by 10 to the minus 2 meters and dividing by 1 centimeter. Right? So 10 to the minus 2 meters divided by 1 centimeter, that is 1. Right? If we don't write the units in, then it's not true. Okay? So this is why it's going to be so essential for us to track what we're doing and to be including our units in all of our calculations. Right? Units should not appear and disappear just because you want them to, right? So the units in this problem are changing from centimeters into meters, not because we magically wanted it to, but because we multiplied by something that was equal to 1 that had those units in it. And those units were arranged so that the centimeter units cancel. We've got 1 centimeter unit in the top and another centimeter unit in the bottom, and they cancel just like algebra variables. And we have a unit of meters in the numerator that sticks around. Right? And when we're all said and done to 2 significant figures, we have 0.095 meters, okay? Or 9.5 times 10 to the minus 2 meters. Okay? The numbers in our metric conversions are from definitions, so they are exact numbers. They have infinite significant figures. So infinity is always going to be bigger than anything else in our multiplication problem. So we're going to be limited by our two significant figures in our starting value. So that was a pretty effective way to do it. But what if we set it up the other way? What if we took our conversion factor of 1 centimeter equals 10 to the minus 2 meters, and suppose we put it in our problem the other way around. So suppose we entered it in, right, as 1 centimeter divided by 10 to the minus 2 meters. It's still equal to 1. So it's still valid. That's still a valid thing to do. My cupcake still isn't changing size over there. But look at what the unit, what happens when we look at the units when we're all done with it. We end up with units of centimeters squared per meter, which is, again, true, valid, not helpful, not really informative, because nobody knows what a centimeter squared per meter looks like. But that cupcake is 950 centimeters squared per meter tall. Again, true, valid, not helpful. So we want to be careful. We're not going to be able to cancel our units unless they are the same in the numerator and in the denominator. So the example we just did doesn't have those units of centimeter canceling out and leaving us with units of meter, if that was our goal. So this almost bottom one was going to be the more helpful way of using our conversion factor in order to change our units from centimeters into meters. We chose the conversion factor, 1 centimeter equals 10 to the minus 2 meter. It connects our two units of interest, and then we used it in a way that worked in our problem. Given what we started with, we wanted to arrange that conversion factor on purpose so that the units of centimeters canceled and the units of meters stuck around, right? So we can use this technique even when the units get a little more or a little less familiar, I should say. Okay, so the bottom one again, true, valid, not helpful though, not what we were trying to accomplish. Right? So if you accidentally had set that problem up wrong, not even wrong, just sort of as the bottom way, you would see that the units you're going to get at the end of the problem are not the units that you were probably asked to find. Right? So you can almost sort of self-correct at that point. You can see just from the units that something isn't quite right. So that's, again, something to practice with, right? It's knowing where to put your eyes. I will probably say that 20 more times this semester, right? It's all about knowing exactly where to look. That's why I can look at a problem and immediately tell what's going on with it, right? You're new at this. Be kind to yourself. You have no idea where to look. You're just looking all over the place. All of these numbers and symbols and units are kind of everywhere, right? So we're gonna try and focus on how do I focus my eyes? Where am I gonna look one sort of step at a time in these problems? That's how we're gonna work on getting more efficient, right? So again, it's just I've been doing this for hundreds of years. So I know exactly where to put my eyes. I know exactly how to look at those units. You're just not used to that yet. So we will work on that. That's what this whole first week, first chapter is about. Practicing looking at those units in the context of these calculations. All right. So that was a nice, slow beginning to all of this. All right, let's put it together how we're going to actually solve these problems. We've kind of hinted at it a little bit here, just sort of showing how the units cancel out, how we're multiplying by 1. But the question is, well, how do I get from the problem to the answer? What's all the thinking that needs to happen in the middle? So let's diagram that out and see what we're going to do. All right. This is our process here. We are going to use this problem solve, and definitely in the slides, I'm going to show you this problem solving process without fail every single time. When it's the appropriate way to solve the problem. We are gonna go through these 5 steps every single time. You may feel, again, if you've had experience with this, that you want to just sort of jump ahead and just jump right to the calculator part. I'm going to challenge you to make sure that you can sort of document and communicate your problem solving strategies here by not skipping any of these steps. Definitely not at the beginning. Let's just kind of work on developing that again so that when the units and the relationships are getting more complex, right? Getting a little more challenging. We're getting multiple steps in our problems. You're going to be able to fall back on this process because it'll be so ingrained in us. You'll always be able to at least get started on the problem because you'll have a plan to follow, right? These 5 steps to go through. So identify is our first step. So we have to read the problem, right? Life is full of story problems, right? Some of them are going to be straightforward, especially these early ones. It's going to be pretty straightforward what to do. And as the situations, the chemical situations get a little more complex, there's going to be more words. There's going to be more things to sort through, and it's going to be less obvious. But we're going to identify what we start with, right? What's our gecko? What's our cupcake? What do we know at the beginning, right? And what's our goal? What are we trying to do with that? What are we trying to relate it to ultimately at the end? Right? The second step is the thinking step. It's the hard. Well, I guess we would call it the hard step, right? It's the one where we have to put together all the information that we have, right? So knowing some of that information, having things memorized well that we're supposed to have memorized, is going to help us recognize what those connections are. It might be more than one step. We might have to hook together a bunch of the conversion factors or the relationships that we've learned, memorized, looked up. We might have to hook them all together. That's the thinking part, right? So that's the part where it's probably going to be the long step, right? Or the step that you feel isn't coming as quickly as the others. And that's okay. That's what it's supposed to be. So again, until we get used to those relationships and what they are and be able to find our way quickly from one to the other, right? That's going to be the step that takes a little bit, right? So if you remember learning how to drive, if you're a driver, right? You had no idea how to get from point A to point B, right? But after doing it a while, you can probably almost do it in your sleep, right? If you keep driving over the same routes. That's what all the practice is going to do here. We're just going to drive over the same routes. We're going to solve the same kind of problems many times, and they'll become automatic. So we can build on them and add to them and use them in different contexts, right? So be kind to yourself with that planning part, right? Again, some of them are going to be more straightforward than others, and you're going to see that connection more readily than others, right? But some are going to take a little more thinking. And we'll kind of do some examples about how to approach those problems and plan. I will tell you right now, you do not have to plan from left to right. That is not a requirement. Sometimes you're going to start at the end of the problem and work your way backwards. Sometimes you'll start in the middle. Sometimes you can see your way to the end from the beginning, but not always. So there's no one right way for that plan. Then we're going to show our work, right? Kind of like the math we saw with our cupcake and our gecko. We're going to show the work with our units. We're going to show how the units are related to each other, how they're arranged so that they cancel out. And then finally, we will pick up our calculator, operate it correctly, right? That's our skill from way back. And then we'll report our answer with the right significant figures and the right units, right? So you practice some of that on developmental practice 2, right? So we are definitely putting all of our skills together at this point. Okay. Alrighty. So just another reminder, planning does require your brain to have space to kind of roll those ideas around in. So again, I'm just going to remind you again, the things that you need to have memorized, let's work on that. So right now, those are the metric prefixes at this point. That's about all we've got going on. So we're going to use some today. If you don't have them memorized yet, right, put that on your list of things to work on very soon. We'll have to have those without having to look them up every single time. We just want to get more efficient with that. So our brain isn't always trying to remember what the milli prefix means. It should become automatic, right? And then our brain has more room to do all the other planning for those more complicated problems. All righty. Oh, here they are. Let's remind ourselves what they are. We've talked about them now. So the ones with the stars are the 9 metric prefixes that you're expected to know. I'm going to encourage you to remember them, not necessarily the way they are on this chart, but as a sentence, right? As a math sentence. 1 deci whatever equals 10 to the minus 1 whatevers. 1 centi whatever that unit is equals 10 to the minus 2 of whatever that unit is. Put in some, real examples if you want. You want to put in units of liters or grams as your base unit there. Also underneath that heading is 1 milliliter equals 1 cubic centimeter. That's good. That's a useful thing to know. That is true. It's going to be real helpful when we need to change units of volume. Some units of volume have things raised to powers and some don't. If you forget that, you're going to feel like you're stuck and you don't know how to get from one to another. It's an awfully boring conversion, but it's an essential one. What's at the bottom of the box there, I'm going to encourage you to, I don't know, take a screenshot or a little picture of that. Those are the conversions from the metric system to our horrible, dumb American imperial system of units. So 1 mile is equal to some number of kilometers. 1 inch is by definition 2.54 centimeters, and 1 pound, all of that number of grams. Those are exact numbers, right? If you use them exactly just like that with all those decimal places, they have infinite significant figures. If you get lazy and round them off, then they're going to have a limited number of significant figures. Okay. So for example, if you only said 1 mile equals 1.6 kilometers, now that only has 2 significant figures. But if you use it as 1 mile equals 1.60934 kilometers, that's infinite significant figures. Right? So we will see those again, right? They're gonna come up again, but this is our slide to remind you of what should be memorized for this chapter. Those 9 metric prefixes. 1 milliliter equals 1 cubic centimeter. For those of you who are in the health field, the cubic centimeter, that's the cc's, right? So if you hear that in the medical programs or in the offices that you're working with, 1 cc is 1 cubic centimeter. That's where that comes from. It's easier to say 1 cc than 1 milliliter. Milliliter is mushy. It rolls around on your tongue. So in an emergency setting, 1 cc is very clear. All right. And again, that information at the bottom is the provided information. You do not have to memorize that. That will be given to you. It'll be on the front of your test. Okay. Any questions on that so far? Okay. Let's just do it. Let's just grab an example and work through all of those steps of the process. Yes. And yes, the periodic table will also be provided. You will have a beautiful version of the periodic table in lovely bright colors so you don't lose it when we finally get together and I give you your purple folders. So yes, you will always have the periodic table and you will always have whatever information I promise I'm going to provide for you will be there. I will send you a picture of the front of the test before we take it, so you can know exactly what's being provided and what you need to work on. Okay. All right. Here's our problem. All right. Lots of blank space, lots of room for you to practice. All right. You can see I've already got it sort of templated out how to solve this problem. Okay. All of our problems are going to look like this. There's going to be the question, and then there's going to be something that looks like your start, your goal, what's your plan, and then we'll solve it. We'll do the math at that point. All right, so let's look at our story. And a little cup of cocoa, and it has 493 mg of potassium. And you want to convert this mass of potassium into grams. All right, so what are we starting with? What are we given? What's kind of right in front of us? It's usually something you can see or feel or touch. What do we know at the beginning of this problem? Yeah. Oh, good. Oh, I like that you even put the material on there. Yes, we have 493 milligrams. right? That is essential, but of potassium. Yes, that's the important part. Yeah, so we can actually start right now developing that habit of writing the number, the unit, and the material. Okay? That's a good thing to start right now. Now, in this problem, we're not changing. We're going to talk about potassium at the beginning of the problem and at the end. So that's not changing. Um, so I don't think I might have written it down, but you should probably write down 493 milligrams of potassium. Does anybody know what the symbol for potassium is? The chemical symbol. It is K. Perfect. I was gonna say, if we were in our classroom, you'd all just peek over at the periodic table and you'd be fine. So it is K. Yeah. Very soon in chapter 2, you're gonna need to know the names and symbols of the first 36 elements, which sounds a lot, but you probably already know about 20 of them. So it's not as much work as it sounds. But yes, potassium is K. So feel free to use that as an abbreviation right now. All right. So what are we trying to find? We know we start with 493 milligrams of potassium. What are we trying to figure out? What's the question? That's our goal. Yeah, good. We are trying to find grams, specifically of potassium, right? That's our question. Convert what we start with into grams of potassium. So in our plan here, right, we've got 493 milligrams, and you could write a K after that for potassium. All right. Um, One thing I'm going to remind you of is to be real careful with your capital letters and your not capital letters. It makes a difference, right? A capital M as a prefix is mega, a lowercase m is milli. We have milligrams here. Potassium is K, it's a capital K, right? It's not a small k. A small k has lots of other meanings in chemistry. So we want to be real precise with our penmanship, really, right? Which is why typing is terrible because it likes to autocorrect and make things not what they are. So 493 little m, little g for grams, and then a big K, that would be potassium. All right, and our goal is grams of potassium, if you want to put the K for potassium there as well. So now we have to think about our plan. Well, how am I going to get from here to there? So it's kind of like planning a trip, right? I'm starting here, I'm ending over there. How do I get from here to there? Can I go there directly or do I have to go a bunch of other ways around the block? So, do we know any connections or conversions or relationships between milligrams and grams? So, we're searching our brains now. Do we know of anything that relates milligrams to grams? We have this chart, right? We can always get from a prefixed unit to the base unit or from the base unit to a prefix unit. That's what these metric prefixes are doing for us. There are connection between a unit with a prefix and a unit without the prefix, as long as they're the same base unit. So what that means is, yes, we do have a connection. We do have a relationship directly from milligrams to grams. Okay? And we know that because we've memorized it, right? Okay? Or we've peeked at our chart, right? Because we're still new at it, right? So what I like to do is I like to draw these little plans so it looks like I'm going to take this unit and I'm going to change it into something else. And if there's multiple steps, right, then I would change it into, I just keep going. So we're going to take our milligrams and we can do this in one step. And under that arrow, every one of those arrows is a conversion factor. I should be able to write down what the relationship is between the unit at the left of the arrow and the unit at the right of the arrow. Yep. And I'm going to write it just like my math sentence. Yep. I'm going to write exactly what that definition of milligram is. So see, a couple of you put it in the chat box already. Yep. So 1 milligram equals 10 to the minus 3 grams. So it's not 10 to the minus 3 is not the conversion factor. That's not helpful, right? We have to have two things that are equal to each other. And we want to have the unit on the left and the unit at the right represented in our equation on either side of that equal sign, right? So 1 milligram equals 10 to the minus 3 grams. When we go to solve the problem, we're going to use that. We're going to use our brains, right? And we're going to arrange that conversion factor in a way that's going to solve this problem. That's going to get us moving in the direction we want to go in. Okay, so let's do that. Let's act out that plan there. So I'm going to start with my 493 milligrams. And then every one of my arrows, every one of those little steps in my plan is going to be a set of parentheses. It's going to be a multiplying by 1. I have to have my numerator and my denominator have to be the same. They have to be equal to each other, I should say. All right. So now we have a choice. We have that 1 milligram is equal to 10 to the minus 3 grams. Well, that's great. We have two ways we can arrange this. We can put the 1 milligram on the top, or we could put the 1 milligram on the bottom. So what do you think is going to be most helpful? Do you want to put the 1 milligram in the numerator or in the denominator? Top or bottom? Awesome. Yeah. I mean, we could put it in either place, but remember, we're trying to get rid of the unit of milligrams. So we are going to be on purpose trying to arrange it so that the milligram units will cancel each other out. The milligrams is already in the top. So if we can put the milligram part of our conversion on the bottom, then we're going to be in great shape. So we're going to, on purpose, choose to use our conversion factor, right? They're equal. 1 milligram is the same as 10 to the minus 3 grams. We could put either one on top and the bottom. We would be multiplying by 1, but only one of the ways of arranging it is going to be helpful to end up with units of grams. So we will put our 1 milligram on the bottom, right? Be real careful with your conversion factors, right? We definitely know the milligram unit wants to go on the bottom, but the number that's with the milligrams in our conversion factor has to stay with it. So the 1 has to stay with the milligram, right? You can't just put 10 to the minus 3 milligrams down there. You'll have changed your conversion factor. And then the 10 to the minus 3 grams, right? That number and unit have to stay together, right? So for that math sentence, 1 milligram equals 10 to the minus 3 grams, right? We have to pick and choose, right? How we want to arrange that. So we can't scramble up the numbers and the units, right? That's going to change it and it's not going to be equal to 1. Right? Knowing those conversion factors, knowing that they're true, right, becomes a little more challenging when we get to the part where we have to figure out what those conversions are, where we're putting them together from other things that we are learning. Right now, it's from a definition. Okay, and now we're done, right? We've set that up. Now we can pick up our calculators, right? And remember how to enter things in our calculator that have powers of 10 in them, how to use scientific notation on our calculator. All right, so let's do that. Remember, if the number's in the numerator, we're going to hit multiply. If it's in the denominator, we're going to hit divide. And we're not going to do any multiplying or dividing by 1, because that is a waste of time. All right, have we got a result? Yes, yes. So however you want to enter 10 to the minus 3 in there. I like to enter it as 1, and then my EE button raised to the minus 3 power, right? Sometimes it's easy to remember that that is just 1,000th, right? So 0.001, that's also equivalent. All right. So before we get crazy, we should check that our units actually cancel out, right? They don't cancel in form grams because we want it to be grams. I mean, we definitely want the answer to be grams, but just because we want it to be grams doesn't mean it is. We should develop the habit, right, of checking that our units cancel. I noticed on a couple of folks' papers on developmental practice 2, you had some units that you canceled, I think, just because you wanted them to. You felt like they should go away. They don't. They only cancel, right? Just like X's and Y's in algebra, if they're exactly the same on the top and the bottom, right? So our milligrams unit, the way we've arranged it, actually cancel in this case. And the unit we're left with is grams. Right? So that becomes part of our answer. Take a look at your calculator. Did your calculator keep track of your units at all for you? I hope not. That would mean that our calculators have become sentient, and we probably aren't ready for that. All right, but your calculator's not doing that part. Your calculator's only doing the numerical part for you. Okay? It's also not keeping track of significant figures, right? So just we thought we were done, but we're not, right? We need to take a look at our significant figures and decide how many should be in our final answer, right? Take a look at it. So how many significant figures are in 493? Very good. So that part has three significant figures. Awesome. Right. Now we've got to look at our conversion factor. How many significant figures are in that conversion factor of 1 milligram equals 10 to the minus 3 grams? Oh my gosh. There's crickets. It certainly looks like there's one. As everybody's looking at it, like, it looks like one. That seems unreasonable. And it is. Because again, we have to think about where did that conversion factor come from? It came from a definition. That means that our conversion factor, 1 milligram equals 10 to the minus 3 grams, is an exact number. And exact numbers have how many significant figures? Right. Yes, infinite, right? It's never going to limit us, right? We're not going to be limited by 1 milligram equals 10 to the minus 3 grams because by definition, there's no uncertainty in it. So any uncertainty, right, any limit to our answer has to come from other numbers in our calculation. Awesome. Perfect. Right. So we've got three significant figures and infinite significant figures. That's what that little sideways 8 looks like. That's our symbol for infinity. Which is smaller, 3 or infinity? Okay. All right. That was not even a trick question. Our beginning number is not always going to be our limiting factor. It often is, because it's usually the thing we measure to get to that. Most of our conversion factors that we're going to use right now, right, in the next little bit, couple days, are going to come from definitions. So yeah, they're not going to limit us. Very soon, though, before we get to the end of next week, we're going to have conversion factors that have limited significant figures. So we should again be working on the habit of checking all the numbers in our calculation. All right. So our answer should have three significant figures, and by golly, our calculator accidentally got it right this time. So good for him. But now we've got our answer, right? So somehow let me know that you've made a decision, you've finished the rounding process. Um, so a box, a circle, a something, right? 0.439 grams, right? Of potassium, right? Put a big K there too, right? And we put a box around it, right? We've got the right value, we've got the right significant figures, we've got the right unit and the right material. And that's when we know that we're done. Okay. All right. So what questions do we have about that process? Right? Okay. Let's try another one and see if that gives us any questions there. All right. So the distance from Toronto to Montreal is 544 kilometers. And of course, that doesn't make sense to our silly non-metric brains. So we want to know, well, how far is that in miles? Like, I have no idea what 544 kilometers is. How far is that in miles? So we'll go through the same process again, right? What do I start? What's my question? We'll make a plan and then we'll solve this problem. All right. So what do we know? What are we given? What are we starting with? What is it that we're trying to convert? Yeah, good. Yeah, so we are starting with 544 kilometers. That's what we know. We know that's how far it is, but we are trying to adjust it, right? What are we trying to adjust it into? What's our goal? Yeah, so our goal is miles this time. Okay. So we want to take our 544 kilometers and we want to figure out what that is in terms of miles. Okay, so our abbreviation for miles is MI, right? We have to be careful. M is meters, lowercase m is meters. MI is miles, MIN is minutes. There's a lot of M's. Some of them are capital and some of them are lowercase. So we, again, need to be very careful with our M's so that we know that what we're doing, right? Because a mile is very different from a meter. Okay, so let's make a plan. Do we have a relationship between kilometers and miles directly, or are we going to have to do some other converting? We're going to have to take more than one step, or is there sort of a non-stop flight from kilometers to miles? We do. We have a definition. So that was again one of the previous slides, one of those bits of information I said I would always give you. One of those conversions is the conversion between kilometers and miles. So yeah, so the question, there's another question, which is a good question. Isn't 1 kilometer just 10 to the power of 3? And the answer is sort of. 1 kilometer is 10 to the third power of meters, though, right? So the base unit has to stay the same for our metric prefixes. So 1 kilometer is 10 to the third power of a meter, not of a mile. So we can't sort of mix and match our base units with the metric prefixes. Only we're just modifying the same unit on both sides. So yeah, so 1 kilometer is 10 to the 3 meters, not 10 to the 3 miles. All right. So yeah, so we can't use just a metric conversion in this case. We have to have some connection between the metric system and our horrible system, which probably means it's going to be a definition and it's something that's going to be provided to you. So that was the one with all the digits in it. So yes, there is a one-step way to do this. Do you have to do it in one step? No, absolutely not. Right. So you can go directly from kilometers to miles. What else could you do? You could go from kilometers to meters, from meters to centimeters, from centimeters to inches, inches to feet, and feet to miles, right? Are we going to get the same answer? Absolutely, right? If we drive all the way around and do 7 different conversions, we should still end up at the same place because that distance is still the same. It hasn't changed. It's still 544 kilometers. It doesn't matter how we change it into miles. It's still going to be some number of miles. Um, so no, it's not wrong to do more or different steps. Right? Sometimes one path or way of getting there is just more convenient or more familiar to you. Or maybe you didn't have this conversion, but you did have the conversion between inches and centimeters. So you went the longer way around. Right? We do that again sometimes when we're driving. We just don't realize there's a shortcut, right? But we know that if we go all this way, we know we're going to end up in the right place. So the same is true with this planning. So there's no one right way to do it. There's only valid and invalid conversion factors, right? So you might have an incorrect or untrue conversion factor. But as long as your conversion factors are all true and you use them properly, we're going to end up in the same place, whether we take 5 steps or 1 step or 37 steps. It doesn't matter. That again is the power of this process. Let's do it in 1 step though, right? Let's do it in the shortest way possible here. So we need to go find what that conversion factor is, which means we need to go look it up and write it down correctly. All right, and it is 1 mile equals 1.609344 kilometers. The way I have written it there, that is the exact definition of what a mile is. Okay. It's no longer defined by whatever silly way it was defined before. It's defined in terms of our beautiful metric system. So if we use all those digits, then we are using an exact number with infinite significant figures. If you round it off, if you use 1.609 kilometers equals 1 mile, then you've limited yourself and you only have 4 significant figures. That might be more than enough for the problem, that's fine. But just realize if you're not using sort of that full defined version, you're going to have a limited number of significant figures that may impact your final result. Okay, so we've identified where we started, where we're going. We've got a plan to get there. We need to solve it now, right? So we're going to do the same thing again. Every one of our arrows is a multiply by 1 step, right? So in ours, we've only got 1 step. We're going to have 1 set of parentheses. All right, we've got our 544 kilometers at the beginning. Right, now we need to think, where do I want to put my 1 mile? Do I want my 1 mile in the top or in the bottom? Oh my goodness. All right. That's a lot easier to think through than do I multiply or divide, right? Which direction am I going in, right? We're just totally letting the units do 100% of the work here. All we had to do was know what that conversion factor was. And now the units are going to go, okay, I'm going to tell you how to use them now, right? You're going to put the miles on the top because that's what you want to have stick around. And you're going to put your kilometers units on the bottom because that's the unit you want to cancel out. You're like, great, thank you, units, right? The units are really our friends here. They're helping us do this problem so we don't have to go memorize every single type of problem and whether we are multiplying by some value or not, right? If we had given you a slightly different algebraic version of this conversion factor, it would work exactly the same way. You would let the units do the work, even if it was in an unfamiliar form to you. That, again, is the power of this method, right? So writing it down, really helpful, right? Trying to do it all in your head, probably going to get jumbled up when we get to be more than 1 step. All right, so on the top, we're going to put miles on the top. I think that was our agreement, right? Which means we're going to put our kilometers on the bottom, right? Note how I've kept the number with the unit, right? That was true from our math sentence or our conversion factor up at the top. That's one reason I like to write them down, to make sure that I've written them down correctly, that I haven't accidentally gotten the numbers swapped. The act of sort of writing that down again gives you another chance to check, did I write it down correctly? Did I remember it correctly? Did I transpose the numbers? Did I get the right power of 10 in there? And no, you do not have to memorize this conversion factor. This is one of the ones I will give you. So any of those conversions between our horrible system of units that we use here and the metric system, I will give you. You may practice them enough, I hope, over the next few days that they're stuck in your brain anyways, but you don't have to memorize them. You don't have to worry about them. All right. Did you check that the units are right? Did you check that, in fact, you have units that are going to cancel and not combine and make things worse? Right? Did you set it up correctly? Right? You can see our units of kilometers, right? That number we start with is sort of effectively in the numerator. So our kilometers units are going to cancel. We're going to have our units of miles left over. We can pick up our calculators now, right? After 7 minutes of talking about this problem, we can finally actually put the math in there. All right. And yeah, again, our units of miles are there. So our calculator has given us all of these digits. And you're like, great, thank you, calculator. All right, clearly that's not what we're going to write down. That's clearly not the right answer. So we're going to, again, right, now that we let all the units do all the work and then we let our calculator do all the work, we have to jump back in with our brains and apply the significant figure rules properly. All right, so we are multiplying and dividing here. So we need to focus on number of significant figures. All right, so which means we have to count numbers of significant figures. How many significant figures are in 544? All right, great. Yeah, it's not a problem when there's no zeros. It's a little more straightforward. Awesome, perfect. 3 in our first one. How about in our conversion factor? How many significant figures are in our conversion factor? 1 mile equals 1.609344 kilometers. Yep, it 100% looks like there's 7. But remember where this conversion factor comes from. It comes from a definition of what a mile is. So since it's a definition, that means it's an exact number, no uncertainty, and infinite significant figures. Yep. All right. So 3 significant figures and infinite significant figures. Which is less, 3 or infinity? Yeah, correct. 3 is definitely less than infinity. So can you now, your next job then, now that you've applied the rule and decided what should be there, your next job is to round that number that your calculator gave you to 3 significant figures, right? So you're going to start on the left and count over 3 significant figures, right? And then look at what comes after that and decide if you need to round up or drop or just drop that off. So we're going to keep the 3 and the 3 and the 8. And we're going to look at what comes right after that 8. Oh, and it is a 0, which means we're going to just let it all go. So we're going to have 338 will be our numerical part of that. But yes, thank you, Brenda. We absolutely have to have a unit in our answer. So before you circle it, right, you're going to write 338 and then the unit. Right? There's no material for a distance. So it's just a distance. So just the unit this time, 338 miles. So not M, because M is meters. That's a whole different thing. Right? And not MIN, because that's minutes. That's not even a unit of length. So we'll have to work our way through all those symbols. Okay. Here's one that's a little trickier. Okay. You're going to convert 65.0. Holy cow, what is that silly thing? What is that weird looking U that looks like it's dripping? Yes, that is our prefix for micro. So that is a microliter. It's one of our metric prefixes. And we want to convert that into nanoliters. All right, so what are we starting with? Where's our starting point? This problem doesn't have a whole lot of story to it. It's a little easier. Yeah, so we're going to start with our microliters. We're going to start with our 65.0 microliters. What's our goal? What are we trying to turn it into? All right, yeah, we are trying to get to nanoliters, right? So this is one of the most straightforward conversions we can do. So I convert this into that, right? You know what your start is and you know where you're going. Yep. All right, so 65.0 microliters and nanoliters. All right, so now we need a plan, right? We need to think about it. Do we have a direct path from microliters to nanoliters? Let's see. So if you've got a direct path, you should be able to write down this equals that with those 2 units involved in it. So there is a path, but it is not a direct path. Okay? None of our metric prefixes are defined in a way that converts from one metric prefix unit to another metric prefix unit. That chart that we had was all defined in terms of how does that prefix unit relate to the base unit, to the unit without the prefix. So we have a relationship between microliters and liters, and we have a relationship between nanoliters and liters, but we don't have a direct connection between microliters and nanoliters, right? There's kind of no bridge that connects those, but they both are connected though to liters. So we're going to have to do this as a 2-step process, right? Because of the way our metric prefixes are defined. All right, so let's see how that looks. So we've got microliters at one end and nanoliters at the end of our plan, right? But there is no direct connection between them. There's no one arrow that connects them. None of those definitions of what microliters or nanoliters mean relates them to each other. They're all related to how are they related to a liter, which is great news, which means that if we just travel to the liters from microliters, then we can travel back out from liters into nanoliters. So let's write down what those definitions are. Give us a chance to practice those metric prefixes again. 1 microliter, 10 to the minus 6 liters, and 1 nanoliter, 10 to the minus 9th liters. All right, those are, again, definitions of what those prefixes mean, right? There is no definition that tells us how microliters is related to nanoliters or how nanoliters is related to microliters. It's all from the prefix unit to the base unit. So the number we're memorizing relates to the base unit. Which means our solving is going to look a little bit different. It's going to look like it has 2 steps this time. It's going to have a couple of things going on with it. Right, so we'll start with our 65.0 microliters. All right, so we'll do the conversions in the order they are and think about how we want to arrange each of those relationships. Each of those, this equals that. So in the first one, do we want to put our 1 microliter in the top or in the bottom? The question is, do we want to put the microliter unit in the top or in the bottom of our first conversion factor? Right, because we're trying to change that microliters into liters. So we want the microliter unit to cancel. It's in the numerator from the number we start with. So we're going to put it in the bottom, which means our 10 to the minus 6 liters is going to go in the top. All right, what do we want to do in the second one? Do we want to put the nanoliters unit in the top or in the bottom? Yeah, good. Yeah, we want to put it in the top. We want the nanoliters to stick around and be in the top. And we also want the liters part in the bottom from our second conversion factor to cancel with the liters that's in the top from our first one. Okay, so if we put our microliters in the bottom, we have liters in the top. So we're going to want liters in the bottom, right? Because we don't want that unit to stick around for forever. We just had to sort of pass through liters on the way to 2 nanoliters. Okay? Double check that your units cancel, right? They only cancel, right, if you can put your fingers on them in the top and in the bottom, and they're identical, right? So microliters will cancel. We've got a liters in the top in blue and in the bottom in green, right? And we have units then of nanoliters left over. All right, now we've got to put this in our calculators. Right, now it's a little more challenging when we've got powers of 10 in the top and in the bottom and they're all over. That's when we have to be extra careful. Make sure we're using our scientific notation feature of our calculators, right? And that we're using it correctly. Right, so we end up with nanoliters. Your calculator should give you a result that looks sort of like this, 65,000 nanoliters. All right, how did we do? All right, good. All right, but again, that's what our calculator gave us. You've got to put your brain back on and think about significant figures. So how many significant figures are in our starting value, 65.0? Right, good. Right, that 0 at the end is significant because there is a decimal point. So it does have 3 significant figures. How many significant figures are in our microliter to liter conversion? All right, got a lot of different numbers going on there. All right, where did that conversion factor come from? 1 microliters equals 10 to the minus 6 liters. came from our little chart, right? Right, which was a definition of what those prefixes mean. So 1 microliter equals 10 to the minus 6 liters is by definition what that means. That makes that conversion factor an exact number. So how many significant figures does it have? All right, perfect. All right, it's infinite. All right, now an easier question, I hope. How about the nanoliter to liter conversion? How many significant figures are in that one? Right. Good. Good. For the same reason, it's also infinite significant figures in that last one. So 3 significant figures for the value we start with, infinite significant figures for our 2 conversion factors that come from definitions. That makes them exact numbers, no uncertainty, infinite significant figures. How many significant figures should be in our answer? Right, the smaller of all those values. So 3. So can we round that to 3 significant figures? All right, so be careful that when you round, you don't lose any of the value, right? You might need to put it in scientific notation, right? Because remember, look, it's a big number right now, 65,000, right? So when you round it, it shouldn't shrink down to 650, right? That you're like, well, that can't be. Scientific notation is going to help here. That's one way to do it. It's always challenging when we have to round on the, on the left side of the decimal point. Yeah. So 6.50 times 10 to the minus 4, right? Or if you want to do it the old-fashioned way, if you just underlined the last significant 0, right? So we can't just put a decimal point at the end there. That would make all of the zeros significant. And we can't leave no decimal point, then we'd only have 2 significant figures. So we have to do something that shows one of those zeros is significant and one of them is not. And 2 of them are not. So scientific notation is probably the clearest way to do that, but underlining also works. Alrighty. Okay. All right. So what I would like to do is do just 2 more problems. I'm thinking if we skip a little break, if we don't do our little break, we can just do these 2 problems and then hopefully be done a little bit early. Does that work for you, or do we absolutely need to get up and stretch our legs right now? Awesome. So let's do these 2 more. I'm seeing any challenges here. Let's do these last 2 problems, which are a slight variation on this. Um, just, yeah, to make sure that we can try those out. All right, so we'll skip our little frog for a minute. Um, right now you have enough information to do developmental practice 4, which is just sort of on the basics of dimensional analysis. It's not due till Sunday, but that might be something, again, if you want to practice something right away. It's going to go through the same process again. Going to kind of help walk you through the start, goal, plan, solve process. All right, so let's try for this one. Convert 65.00 feet into centimeters. Right? Think about where you're starting, where you're going, and then how are you going to get from where I start to where I'm going? That's going to involve knowing what sort of tools or what sort of conversion factors you have available to yourself. And again, there's more than one way we can do this. You don't have to do it in any one particular way. But we will get the same answer no matter how we do it. All right. What are we starting with? Awesome. Right. 65.00 feet. And where are we going? What are we trying to find? centimeters. Perfect, right? So again, sort of a more or less straightforward kind of phrasing of that question. All right, what's your plan? How are you going to get from feet to centimeters? There is no direct conversion. If you Google, you will find a direct conversion, but Google will not be with you. So you need to be able to develop plans based on conversion factors that you know or will have access to. All right. So yeah, I've got a couple of different plans going on there. So it depends again on what conversion factors you know or have available to you. Um, I obviously my slides are pre-done, so I've already picked one way to do it, but you can go ahead and do it a different way and prove that you get the same answer. I have gone from feet to inches and then from inches to centimeters. Inches to centimeters is one of the conversions that I'll always give you. So that'll always be right on the front of your test. If you went a different route, right, feet to meters to centimeters, that's great. I'm not going to give you the conversion from feet to meters, but if you know what it is, good for you. Go ahead and use it. As long as it's correct and true, we will end up in the same place. All right. So I can do what I usually do, which is write underneath my plan, my steps. Each one of those arrows is a conversion factor. So I should be able to write it as something equals something, where the units on either end of my equals are the units that my arrow is connecting. So I know that 12 inches equals 1 foot. That involves both units in that first blue arrow. Okay. And I know because it's going to be given to me that 1 inch is defined as 2.54 centimeters. Now I've got all I need to know, right, to go ahead and then act out this or solve this problem. And I'm going to let my units do 100% of the work and tell me how to arrange the math. And then my calculator is going to do the math. And then I'm going to deal with significant figures. All right, so I've got 2 steps planned out. You may have planned out more steps depending on your route, but mine has 2 steps in it. All right, where do I want to put the feet from my first little blue conversion? Top or bottom? Some good, right? Because we want that unit of feet to go away. We want to change it into inches. I'm going to want to put the feet unit of my conversion in a way that will on purpose make it cancel out. So I'll put the 1 foot on the bottom and the 12 inches on the top, right? How about for my next one? Do I want to put the inches in the top or in the bottom? Right, good. In the bottom, right? Because again, we want to on purpose make those inches units, turn them into centimeters. We don't want to have them around anymore. So the way to do that is to have that unit across from, right, or opposite where that unit is elsewhere in the problem, right? So that means our 2.54 centimeters has to be on the top, right? Double check that your units are arranged so they actually cancel. Don't just cross them off because you want them to. Cross them off because they are actually one on the top and one on the bottom, right? So our feet are arranged that way and our inches are arranged that way. And our centimeters are what's left over. That's a good sign because that was our question. How many centimeters? Okay. Now we pick up our calculators, enter all those values in, right? And our calculator gives us this great big number. And now we have to round it to the right number of significant figures, which means we need to know how many significant figures are in everything in our problem, right? So how many significant figures are in 65.00? Awesome, good. Good. 4. And how many are in 12 inches and a foot? We're not fooling anybody anymore, right? You make that, it's from a definition, so it's infinite significant figures. How about our 1 inch and 2.54 centimeters? How many significant figures? Okay, good. See, now we've got it. Infinite. Yes, that is also from a definition of what an inch is. So we've got 4 significant figures and infinite significant figures. How many should be in our answer? Great. All right. So I'm seeing a lot of fours, which is perfect. So can you round that number to four significant figures? You can put it in scientific notation. You can leave it the way it is. That is 100% up to you. This problem did not say do it in a particular way. All right, great. Good. I like that we put our answer with the unit as well. Yes. 1,981 centimeters or 1.981 times 10 to the 3 centimeters. Either way is completely fine. Okay? And if you went another route, you should get the same value. Again, assuming you used correct conversion factors that were true and you use them properly. Awesome. All right, let's do one more that has a little twist to it. So we'll leave you with that different way of thinking about it. All right, here's our International Space Station. It's in orbit, out in outer space or almost outer space at a distance of 370 kilometers. How long in seconds does it take for light to travel from the Earth to the International Space Station? And I will tell you that the speed of light is by definition 2.9979248 times 10 to the 8th meters per second. Okay. There's a lot more words in this problem. Let's just approach it the same way we did the other ones. What am I starting with? What am I trying to figure out? What do I know? Good. Yeah. So we know what that distance is, right? And we're going to try and relate that to what? What are we trying to find out? What are we trying to say is related to that distance? Right? What's our question? So we're going to start with 370 kilometers. And what is our goal? What are we trying to find out that is somehow connected or equivalent to or related to our distance? Okay. So we already know what the speed of light is. So that's not our goal, right? If that was our goal, we'd be done. So our goal, what does the question say? Let's go find the part of the problem with the question mark. Yes, we want to know how much time, how long. We're in seconds. So we're looking for seconds in this case. But you're right, that speed of light is somehow related to all this, right? Because it matters, right? How fast are you going? That's going to be related to how long it takes. We know there's a connection between distance and time, and that connection is how fast you're going, right? Right? You know, if you go faster, it's going to take less time, right? We know that, and that's true of everything. Light just happens to go really fast, right? That's what speed is. It's a connection or a relationship, a conversion factor, if you will, between a distance and a time, right? So if you were going 40 miles an hour, that's telling you there's an equivalence there. Every 40 miles is going to take you 1 hour to drive, right? 40 miles equals 1 hour, right? With the speed of light, it's just a whole lot faster. It's 2.9979248 times 10 to the 8th meters. That's equivalent to 1 second. So it goes really far in 1 second, right? But that's a conversion factor. It's a conversion factor between meters and seconds, right? So we could write that as a math sentence, right? 2.9979248 times 10 to the 8th meters equals 1 second. That speed of light is a conversion factor, not our start, not our goal. It's maybe something that we're going to use in our plan to get us from meters to seconds or seconds to meters, depending on which direction we're going in. All right, so let's write that out. Okay, we're going to start with 370 kilometers, and we're trying to connect it to, well, how long in seconds is it going to take to go that far? if we're moving at the speed of light. All right, so we need a plan. Do we have a connection between kilometers and seconds directly? The answer is no. If you look at the speed of light, yep, it's telling you the connection between meters and seconds. So you're like, huh, well, if I could get to meters, then I could definitely get to seconds because that's what the speed of light's going to help me do. So you see, we're not necessarily developing this plan from the beginning. We're kind of almost approaching it sort of in the middle or from the end. We know we can get from seconds to meters because that's what the speed units are telling us. That's what we know. So can we get from kilometers to meters? Do we have a connection there? We do, because that's a metric prefix, kilometers and meters, right? That's what those definitions from that chart that we're supposed to memorize is telling us, right? So we can go from kilometers to meters, right? And we knew we had to head towards meters because the connection we had to the unit of time, our speed, had units of meters and seconds in it, right? So again, kind of by using those units, we've sort of fumbled our way into a plan there, right? By thinking about all the relationships we have at our disposal, right? So speed is a great connection between a distance and a time, between a very specific unit of distance and a very specific unit of time that may or may not be the ones that you have in the problem. So in this case, we had to get our distance into the right units, meters, so that we can use our speed. So let's write down again underneath, just to kind of keep our pattern going, right? What those conversions are. So 1 kilometer equals 10 to the 3 meters. That's again, by definition, that's what that prefix means. The kilo prefix means 10 to the third. So 1 kilometer is 10 to the 3 meters. All right. And from meters to seconds, that's when we're going to use our speed, right? In fact, any unit that looks like this, with a unit on the top and a unit on the bottom, right? You can always write it as that number of the top units equals one of the bottom units, right? We're going to see that next time. We'll see lots of units like that. All right. So our conversion factor, then if we wrote it like a sentence, like a math sentence, 2.997924458 times 10 to the 8th meters equals 1 second. Again, that's not something you have to memorize. That's something I would provide for you. This version of the speed of light is the definition value. If you start, again, if you start rounding it off, then you may have less, you will have some limited number of significant figures. When we use it like this, it's got infinite significant figures. Okay, so now we can, right? We've done the hard part. We've done the planning. We've got to do the easy part now. We've got to put it together, right? And do the math part, right? And the units are going to help us put it together. And our calculator is going to help us do the math part. And then we're going to have to remember our significant figure rules. Pop back in with that. Okay, so let's start with, again, we've got sort of 2 conversion factors here. So we have 2 steps in our plan. So we'll do them just one at a time. Do you want to put the kilometers from the first conversion factor, the blue one, in the top or in the bottom? All right, good. Good. Yep, it's going to go in the bottom. All right. And how about in the second conversion factor? Do we want to put the seconds in the top or in the bottom? Yeah, good, right? Because now we've got some meters that are in the top that we want to go away. We don't want them there at the end. So we'll put our meters in the bottom, our seconds in the top. Now we're gonna, again, the units did all that work for us. We had to do the work of knowing what the relationships are, making sure they were true, right? And understanding how we could link them together, right? That's where we're using our brains. The units are gonna do the work after that. Then our calculator, we're gonna pick that up and operate it correctly. Be careful, there's powers of 10 in the bottom, a scientific notation in the bottom. Make sure you're using that EXP or EE button on your calculator. That'll avoid errors in powers of 10. All right. And we're going to check that our units cancel before we get too far along. Right? Our kilometers cancel, our meters cancel. We have seconds left over. All right. This is what my calculator gives me. Oh my gosh, so many digits. Right? I put the units over there. All right. How many significant figures should be in our answer? Well, we got to go figure out what we use to get there. So how many significant figures are in 370? Yeah, okay. How many significant figures are in 370? Yeah, so not 3. There's no decimal point there, so that 0 at the end is not significant. So only 2 in our first number. How many are in our kilometer to meter conversion? All right, awesome. Infinite, because it's a definition of what the kilo prefix means. And how about our speed of light? How many significant figures are in that one? It's also infinite because it is by definition. That is the value we have settled on. All righty. So we've got 2 and infinity and infinity. How many should be in our final answer? Right, yep, the smaller of that. So 2 is smaller than infinity. Can you round that to 2 significant figures? You can leave it in scientific notation. You can turn it into a decimal form. That is 100% up to you. All right, so 1.2, that's our 2 significant figures, right? We're just going to let it go, right? It's a 3 that comes after the 2. 1.2 times 10 to the minus 3 seconds. Okay, so as promised, we are going to stop right there. Those are our 2 extra problems. That are 2 extra problems? Yeah, those are our 2 extra problems. We are a little bit, like I said, we've done a little bit of Monday's work, but on Monday we're gonna carry on with more of our dimensional analysis, looking at what happens when we have units in the top or in the bottom, or units that are squared or cubed or other weird things. And then eventually maybe get to density on Monday or more likely Wednesday. So we are, like I said, you guys are amazing. I appreciate you all.